All right, go ahead and get started. Welcome to EET 2.3, Advanced Electrical Circuits. So this is our simple syllabus, and for people that are here this morning, it's it's a new thing that they're doing. The nice thing about the simple syllabus is that all the links are updated. It's like online type stuff. So all I have to do is fill in a little specific information for my class, my contact information, things like that. So I got office hours. I'm here Wednesday, Thursday from 3:30 to 5, basically between my classes, and then on Tuesday from 3 to 5 prior to the ET 125 class. So this is a continuation of 113, which is just our circuit analysis. And we're going to get a little bit more in depth here. And we've got a lot more fun things that we can do now that we're adding capacitors and inductors into the mix. So I'll talk more about that as we go through the day by day type thing. So we are using the introductory circuit analysis book, which is the same one that you had for ET 113. Same one. Did you go by Benjamin or Ben? Ben. Okay. I'm not sure what we're going to do, because the problem with that is this book is classes off in the fall, so they don't sell it. Yeah, it's great. So talk about class and see what options you might have. All right, so again, not a hybrid course. I had it on there because we started hybrid when we came back from COVID years ago, but I still leave a lot of stuff online, right? So iCampus is used a lot. So we got a lot of objectives, all right, we're going to get through here. So the schedule of activities here, fairly dry, kind of shows where everything is due, the different homeworks and labs and everything else like that. But not a lot of detail. All right. So today we're basically actually going to backtrack to chapter 8. So if you recall, in 113, I think I did the first 2 sections of chapter 8, which was basically current sources and source conversion. And then we jump right to chapter 9. Right? I'll be doing 113, so I'll kind of go over that again. But we're going to actually go back there, because what we can do in chapter 8, or what chapter 8 had for us, is another way, right? Yet another tool to analyze circuits. As if you didn't have it up, right? But there's more, all right? So we'll come back to that. So after I do my 113 review, I'll actually jump back there. We'll set everything up for lab number 1 and go from there. All right, then chapter 10. Now, I know for those of you that haven't had 113 in a long time, or never, Dylan's the only one that just finished it. Okay. Chapter 10 is capacitors. Well, in 113, all I did was give a kind of a quick 1-hour intro. Hey, here's capacitors, right? Here's the basic concepts. We're going to go a little bit more in depth next week. All right, so I'll kind of rehash a little bit, quick review of it. And then we'll study a little bit more. Likewise, chapter 11 and 12, inductors. Same thing. I did a quick, roughly 1-hour intro in 113 saying, yeah, this is the inductor, this is the coil, this is electromagnetism, right? And all I did in 113 with both the capacitor and the inductor was kind of go over what happens when I apply the DC voltage to an RC or an RL circuit. And what happened, of course, was the capacitor would charge up, or the inductor current would build up, and we have our, what I called our universal time constant. But we're going to delve into that a lot more deeply. We're going to look at the formulas behind it, and actually the ability to solve specifically how much time it takes to reach a voltage, how long it takes to reach a current, what's the current going to be after a certain amount of time, All right, so we'll delve deeper into it for both capacitors and inductors in weeks 2 and 3. All right, so from there, we'll then move into chapter 13, which is where we lay the groundwork for the idea of AC, all right, alternating current. In 113, everything we did was DC. That's it. Everything. Now, for the advanced students that have been here a little longer, all right, they've already had an introduction to AC. Well, I'm going to start kind of from scratch and pretend you don't know that much. So we review for some, new for others. All right. But we're looking at the concept of AC, alternating current, specifically periodic waveforms. All right. That's a big part of what we're going to look at. And then the neat thing about AC and DC is how capacitors and inductors respond to those different voltages. And so we'll lay the groundwork then for what is known as reactance. So when I do my review and we talk about Ohm's law, right, we're going to talk about Ohm's law is for what? Resistance, right? Well, it turns out that for capacitors and inductors, when I put AC on them, they generate something called reactance, which also has the units of ohms. So we can actually apply Ohm's law with reactance. Okay. So you see that in chapter 13 and 14. We'll get into that in a little bit more detail, talk about what reactance is, phase shift, and everything else. And also, this is the fun part, lay the groundwork for the mathematics that we will utilize as we go forward. Okay. Now, I know everyone in here knows how to add, subtract, multiply, and divide. Well, guess what? You've been doing that with real numbers. We're going to add imaginary. We're going to add imaginary numbers because what that allows me to do is do the math in either rectangular form or polar. All right, so you got rectangular coordinates, polar coordinates. All right, so that's where we got to use a little trig, little sine, cosine, tangent to move back and forth between those systems. But we can use that concept to now add, subtract, multiply, divide. But now in complex form. Because what we're going to add to the mix is a phase shift, something we've never had to deal with before. So we lay the math groundwork for that in chapter 14. And then in chapter 15, we just basically jump right in and say, all right, here's what happens when I put these components in series. A resistor, capacitor, inductor. Mixes of those three components in a series circuit. Predict. Just like we did in 113, we're going to predict what we expect to see. All right. Now, the big difference is instead of using a meter, we'll be using the oscilloscope. So, for those of you that have not used an oscilloscope before, we'll get a good introduction. We'll get really good at using it. And even for those of you that have used oscilloscopes before, it's going to be dual channel operation. So that you haven't done before. So it'll be new for everybody. All right. So then we'll have a test in there, chapter 16. We'll basically do all that with parallel circuits. So a parallel resistance, inductance, capacitor circuit. Predict how those are going to work. Build the circuits, make the measurements, just like we were before. Any fact. All right. You missed it. Not yet. All right. And then we'll get into chapter 17, where we will basically look at series parallel combinations. So similar to what we did in 113, as I go over the review here, you'll see that. All right. series circuits, parallel circuits, series parallel circuits. And so now instead of just resistors, we've got that mix of two other devices as well. Chapter 19. So part of my review tonight for 113 is going to include our circuit theorems, right? Superposition, Thevenin, Norton, maximum power transfer. Guess what? You get to do it with AC as well. Nice thing is most of the same rules apply. Notice I said most. One little tricky thing. All right. And then in chapter 21, what is chapter 21? Shoot, I forgot what 21 was. Of course, it would help if I had my book. Oh, there it is. Okay. All right. Yeah, what 21 was. Resonance. That's right. So one of the neat things about circuits that have both capacitors and inductors in them, right, is that whole reactance thing I was talking about, created a phase shift. Well, it so happens that one of them creates a phase shift 90 degrees one way. The other one creates a phase shift 90 degrees the other way. Well, what's that? That's 180 degrees. All right. And so we actually have conditions called resonance where the amount of reactance cancels out. And the circuit becomes purely resistant. That's resonance. You got series resonance, you got parallel resonance, and all kinds of fun things happen when we do that. Okay, so that's chapter 21. We got a fair amount of time to spend on that because we have parallel and series resonance to deal with. And then I touched base on chapter 22, which is filters. All right, and I know for those of you in the morning class today, I said, hey, we're going to be doing active filters. Well, these are passive filters because there will be no active device, just reactive devices, inductors, capacitors, and resistors. And really all this is taking a lot of what we learned as we're going through and analyzing our series and parallel circuits and saying, well, when you build it like this, it does this, right? Low pass filter, high pass filter, band pass filter, band reject filter, all those. All right, then we got another test, final exam, and we're good. Okay. All right, so these assignments that populate, I don't know why they're there. I don't know why they're there and others aren't. I don't understand that. If you go into iCampus itself, all the assignments are there. If you actually go to, I know if you go to the legacy syllabus, there's all the assignments right there. All their due dates, everything. Okay. So it seems like the only stuff that populates is the stuff without a due date. I don't know. That's weird. Anyway. I don't know. But here's some of the other important stuff, right? There's so we got homework. You're gonna have homework every week, pretty much that I lecture. Except for this week. Freebie. It's only free one. All right. 10% of the grade lab assignments, they a total of 25%. I think I have a total of 14 labs for this class. Pretty much almost every week you get a lab, plus a couple weeks you get 2, and might be a week when you get none. Quizzes, 20%, and then what I just say, 3 tests, right? 2 major tests, and a final exam all over 50%. Final grading scale is just 90, 80, 70, 60, 70. All right, so attendance, right? Need to be here. All right, I lecture. Now, obviously, for those of you that have me for a while, know that what happens if you're not here? What do? Every class is recorded. All right. So if you can't make it, right, this time of year, that can happen, right? Whether it be a car that dies on you, doesn't want to start. Okay, bad weather, sick, whatever, right? If you're sick, I don't want you coming in here and making me sick, all right? Lectures will be recorded. There'll be a link up. Usually by the end of the day, the class for this morning, the link is already there. All right, if you want to review this morning's lecture, it's already there. Likewise, so just Don't come in, get us sick. Just stay home, watch the lecture. You'll have time. There's other times that I'm here. You can get in, make up labs if you need to. Okay. All right. Make up if there's a test or a quiz that day, we'll figure it out and get it made up there. All right. I do respond fairly quickly to emails and phone calls. All right. I try. Okay. I got all the apps on my phone, so as long as my phone is charged up and I got it with me, I'm good. I mean, of course, you're committed here. You've got time you're going to have to put in as well. All right. Now, from there on, pretty much this is the boilerplate. Everything's filled in, all the links, all the different things here. If you have any questions, anything you need to look at, support, advising. Well, when it comes to advising, please see me. All right. I've been doing this for 25 years now. I know a whole lot more than anybody else, all right, about this program. Okay. If I can't answer the question, I'll usually be able to point you in a direction where you can get out. Okay. And as I said earlier, so everybody in here was already here this morning. If you're getting close to graduating, yeah, talk to me. All right, if you're not sure where you're at. Okay. Questions on all that? All right, so review. As I said this morning, this review is going to delve a lot more into what we did in 113, simply because that is the only prerequisite for this course. All right, and for a lot of you, you haven't had it in a long time. Okay, which can always be a challenge, right? So, won't be as quick as this morning's 113 review. I'll tell you that. Okay. All right. Okay, so I kind of skipped over the first part of 113, right? The big concepts, right? Current, voltage, and resistance. So those concepts were really what the first 3 chapters of this book covered. Current, of course, movement of charge, right? And our focus in this class, will still be on that, right? The charge that moves, electrons, right? But in the DC standpoint, right, our voltage source, we label, right, this is my DC source. We always have positive, we have negative, and we have some magnitude of voltage. And it was constant, never changed. That's what's going to be fun about this class, is the voltage now will not only change the magnitude, but will also change the polarity, right? That's AC. So in 113, though, we just said, well, that's that, right? And when we hook it up to a resistor, right, provide resistance. Now, the electrons themselves are being pushed through the conductor in that direction. Like charges repel. The negative from the source makes the electrons move away from it. But there's a 50-50 chance, back when electricity was first discovered a few hundred years ago, of them guessing which way current was moving. They didn't know. They didn't know anything about electrons or anything. They just saw this reaction, right? They saw what happened. So they guessed incorrectly. The current went from positive to negative. So that's called conventional current flow. That is what I use in here. All right. So I always like to remind everyone of that. All right. Now, when it comes to AC, well, that means what? If the polarity reverses, that means the current reverses as well, right? Hence, what does AC stand for? Alternating current. All right. Well, that alternating current results from alternating voltage. So I don't know why they chose these. Yeah, whatever. All right. But when we get into the AC part, we'll talk a little bit about that. But we are still going to kind of make an assumption about a current direction. And if the current flows the other way, well, that is just negative current. We're going to have positive and negative currents. Okay. All right. So when we build our basic circuit, of course, we do have Ohm's law. All right. Which says what? Current is equal to voltage divided by resistance. Now, you may recall, all right, I know when I did 113, I talked about this specifically. This author, Arthur's my grandson, sorry. This author, all right, he will mix or he will use both the E and the V to represent voltage. All right, E, of course, is short for what? Electromotive force, EMF, right? Which is basically what voltage is, right? It is the force that moves electrons, electromotive force, right? Backwards, okay? And so you may see this. You may also see this. Now, those two formulas really tell me the same thing mathematically, but the letters kind of distinguish, all right? So what this is telling me is that if I apply a source, usually he uses the capital E when he's looking directly at a source. So I mix it up sometimes, all right? You'll see me kind of go back and forth, all right? He usually uses the V when he's looking at the voltage across a load. Now, in the basic circuit that I drew here, those voltages are exactly the same. All right, they're exactly the same. Because there are only 2 points in this circuit. We'll get to all that here in a second. All right. Now, I said earlier, Ohm's law applies to resistors. Now, here's the neat thing. All right. All that work that we did in 113, series resistors, parallel resistors, series parallel circuits. We'll see that, kind of review here in a second. But it doesn't matter if that voltage is DC or AC when it comes to resistors. It's all the same. It's all exactly the same. So that doesn't even matter, right? This won't get complicated until we add in capacitors and inductors. Right. So if I do this, right, I say, well, what if it's an AC source? There's a resistor, there's a voltage. Well, guess what? The current will still be voltage divided by resistance. Doesn't matter. Now, when we get to chapter 13, we will get into more detail about how we label AC voltages and what we call them, right? How many different ways do I have to measure AC voltage that you've already been exposed to for my advanced students? You don't have to. How many different ways do I have to measure?
Oh, sure.
3 that we use regularly. Peak to peak, peak, and RMS. Now we'll cover all that in chapter 13. So that's all covered. Doesn't really matter. All right. So that's Ohm's law. Now, in chapter 4, we also talked about power. Right? So power, of course, we're pretty familiar with P, and power is calculated by taking current times voltage. Current times voltage. So that's true for any device. Current times voltage. In the case of a resistor, we can use Ohm's law and substitute in. So we can also calculate power by taking current squared times resistance or voltage squared divided by resistance. All that is just taking Ohm's law and substituting our expression for voltage and for current into our power equation. Now, for DC, all those numbers are constant, right? Voltage never changes, power never changes. What happens with AC? Uh-oh. It's changing, right? It's no longer constant. So that gets a little tricky. That's more of what I will cover in chapter 13. Okay. So, more to come, all right? I like to just tease you. Give you a reason to come back, right? Now, again, my advanced students, we've already covered this, right? But it's been a little while. Probably won't hurt to remind you. All right. So that's the first 4 chapters of this book. Now, in the next chapters, then we got into what? Series circuits. Well, I've already hinted that, yeah, we're going to revisit this, right? Except now, instead of just using resistors, we're going to have resistors, capacitors, and inductors thrown into the mix. Okay. So all that's going to change when we get there and start doing that is how we do the math. But the concepts, those all still apply. All right, so just a reminder of what those concepts are. All right, so for a series circuit, what does that really mean? One path for current flow. So components are in series if there's only one path for current flow. So that, of course, means what? Well, that means that all components in series have the same current. What happens with voltage? If I have series components, and there's a voltage applied across all of them, what happens to that voltage?
It drops.
It gets divided, right? It gets distributed among the different components. Well, same thing's going to happen if it's AC, or if it's a capacitor, or if it's an inductor, right? It's the components, all right? Same thing's going to happen. Voltage is going to be divided, okay? All right, so they're going to have what? They're still going to have the same current, exactly, all right? So same current, voltage is divided. Now, in that chapter, we also introduced Kirchhoff's voltage law, right? Kirchhoff's voltage law. What did Kirchhoff's voltage law tell you? Somebody repeat it. The algebraic sum of voltages around a closed loop
It's all added up.
is equal to
All of them.
0.
Oh yeah.
Algebraic sum equals 0. All right. Now, we're going to reuse that today. All right. So you're going to see that again today. I'm not going to spend much time reviewing that because we're going to practice that today. All right. It's going to be an integral part of that advanced circuit analysis. All right. But, right, so real quickly here, algebraic sum of voltages around closed loop equals 0. Okay. So keywords in there, right? Algebraic sum. That means I pay attention to polarity. Okay. Closed loop means I start at one place, come back to that place. Again, we'll be using that today. Okay. All right. When I have resistors in series, the total resistance is nothing more than the sum of those resistors. Oh, here's a neat thing about that. What if it's not resistors? What if it is a resistor and a capacitor and an inductor? Well, it's no longer just resistance, it's resistance and reactance. And guess what? They still add up. Okay? Again, the math just gets more complicated. Or I should just say complex, because we're using imaginary numbers. All right. So that is series circuits. I got room here. Okay. Parallel circuits. Okay. So what does, or how do I recognize components in parallel? All right. Well, they're going to have the same voltage. And we consider them to be in parallel because they're connected to the same 2 points, which is why they have the same voltage. Okay. So for parallel circuits or parallel components, right, connected to the same 2 points. Because of that, they do indeed have the same voltage. Whether that voltage is DC or AC. Okay, it doesn't matter if it's a resistor and a capacitor and an inductor. Well, it doesn't matter. All right, whatever they are. So what happens with current? The parallel components. Current is divided. Exactly. All right. So all I'm doing is just swapping, right? So same current for series, same voltage for parallel. For series components, voltage gets divided. For parallel components, current is divided. Okay. Now, what Kirchhoff's law did we learn about in chapter 6? Kirchhoff's current law. Exactly. Okay. What does Kirchhoff's current law say? Andy, is that your try?
Nothing close.
Algebraic sum of currents at a point. Easy. Right? Algebraic sum of currents at a point equals 0. Emphasize it at 0, not O. Okay, just in case you wonder. And we're going to be using that today as well. Okay, so we're gonna get a review of Kirchhoff today. All right, it's going to be a big part of what we do. The fact is, everything I just reviewed right there, Ohm's law, Kirchhoff's current law, Kirchhoff's voltage law, that's all we're going to use today for that advanced circuit analysis. Literally, that is it, as far as laws and rules go. Okay. All right, now, if I have resistors in parallel, right, their total resistance is the inverse of the sum of the inverses. If I only have 2, I get a special for that, right? I can just say product over the sum. Just like I said for series components. When those components become something other than resistors, like capacitors or inductors, all we do is replace resistance with reactance. And we do. Again, though, the math is a little bit more complex. That's it. All right? That's it. Questions on that so far? So again, primarily review here, right? Reminds everyone of what we've done before. Now, for series parallel, right? I'll just kind of tuck that in here, right? So series parallel circuits, that was chapter 7, by the way. What did we do, right? How did we solve series parallel circuits? How did we solve those? We looked at the circuit, we found resistors that were in parallel or series, and we kept combining them until what?
We got to a smaller schematic.
Till we got down to one resistor, ultimately, a simple series circuit, a simple parallel circuit, or however you want to look at it, all right? And of course, we have the tools to take parallel and series circuits and reduce them to one resistor, all right? So in the end, there can be only one. All right, you guys are too young for that. Okay. Highlander. You know it? Yeah. I love that. Been what, 20 years? Yeah, okay. All right. So that's all we did with series parallel circuits. We just kept combining things until we had one resistance. Well, we can still do that when it's resistors, capacitors, and inductors, except, and this is what I haven't quite said yet. So when you combine resistance and reactance, what do you get? Well, that becomes a third term, which we call impedance. All right. So impedance also has a units of ohms. The trick is, it's a combination of resistance and reactance. All right. And so we go back to that whole complex number thing. All right. Literally, impedance is just opposition to current flow with a phase shift. That's really what impedance is. And if you want to get technical, just to peek ahead, resistance is the same thing. But the phase shift caused by a resistor is zero. Okay. The phase shift caused by a capacitor and an inductor, I already gave you a hint if anybody remembers earlier, 90 degrees. And impedance could be somewhere in the middle. Basic idea, all right? So that's what we're going to be. We're going to be able to do that with resistor. And so one of your labs is literally going to be building a circuit with, I think it's a resistor, an inductor, and two capacitors. I can't remember exactly anymore, that are in a series parallel arrangement. And you will have the tools, you will have the ability to solve and predict exactly what the voltage is going to be across every component. That's where we're going to go, right? That's eventually where we're going to get to. All right. So, any questions on that? All right. Now, from chapter 7, we moved on to chapter 8, where all we did in chapter 8, so we're going to pick that up after the break here, okay, was basically talk about current source, because already we'd introduced the voltage source, all right? And here's the fun part. Just like I can have an AC voltage source or a DC voltage source, I can also have an AC current source and a DC current source. So those concepts are still going to be there, all right? And, you know, this is where I just want to revisit briefly. All right, we won't use it too much in here, but I want to make sure everyone remembers, right? You have two types of voltage sources, two types of current sources. And I don't mean AC/DC. What I mean is what? Ideal and real. My ideal voltage source is just that, right? There's your polarity, there's your magnitude. My ideal current source is just that. I have a direction of current and a magnitude. These are my DC. So what do I do to make them real? I just add a resistor. That's it. For the real voltage source, the resistor ends up in series with the voltage source. And for the real current source, where's the resistor end up? In parallel. Now, why is that significant? Well, because the other thing we did in chapter 8 we learned about was something called source conversion. Because if I put those two things in a black box and I make a whole bunch of measurements, I hook up a whole bunch of different components up to it, what ends up being true? Well, I can't tell the difference between the two, as long as the values match certain parameters, right? So if I want to convert this into a current source, the resistance stays the same, and the magnitude of the current simply becomes the voltage divided by the resistance. That's it. And if I want to convert this into a voltage source, again, the resistance stays the same, and the magnitude of the voltage source simply becomes the current times the resistance. That was our source conversion. We actually use that as a potential method for solving more complex circuits, especially circuits with, for example, two power sources or two sources. It's kind of a way around superposition. So that's still there. We're not going to use it as much, but the concept is still important. Because where does this play into? Well, that plays into chapter 9, which were my circuit theorems. Now, I think chapter 9 contained a total of about 7 or 8 different theorems. All right. Some of which I don't even remember the name of, because guess what? I never use it. Oh, Millman. Millman is one. I remember Millman. I don't remember what it is anymore because I never use it. All right. The reason I covered those 8 theorems was because you're going to see them again. And I think for the most part, for your advanced students, you have. Okay. I'll go ahead and go over those real quickly because just like everything else I've talked about here, it can be applied to AC with capacitors and inductors as well as resistors. I know I kind of glossed over them in the review this morning for the simple reason that I was going to do it tonight. So that's why you get a little bit more in-depth review tonight. All right. Superposition. Superposition theorem allows me to solve a circuit with multiple sources. Right? Multiple sources. Now, 2 steps, right? Still solve. Okay, very good. All right, so we're going to solve the circuit one source at a time. What do we do with the other sources? Comma. Replacing other sources with their ideal internal resistance. What the heck is that? Well, let's go back real quick. ideal. My ideal voltage source had no resistor in series with it, which means the ideal internal resistance of a voltage source is 0. That's a short, okay? So when you redraw the circuit and solve it in superposition, if it's a voltage source, you put a short there. Meanwhile, the ideal current source has no resistor, which, because it's in parallel, in order to make that essentially go away, you have to have infinite resistance or an open. Okay. So when you do the superposition theorem, it's a voltage source you replace it with a short. If it's a current source, you replace it with an open. Good news. Same thing applies to AC sources. Okay, so when we do get to superposition in AC, nothing changes. Okay, a short is still a short, an open is still an open. Okay, so just remind you, right? Voltage source becomes a short, current source becomes an open. All right, now, however many sources there are, you have to do that many times. If there's 2, you do it twice. If there's 4, you do it 4 times. And in the end, you algebraically combine the results. Algebraically means what? You pay attention to polarity if it's voltage, direction if it's current. And if they're both the same, you add them. And if they're opposite, you take the difference. Or you make an assumption about which direction or polarity you have. And if it contributes to that polarity, it's positive. If it's the opposite, it's negative. Then you find all the results. All right. Let's do one quick example. All right. The reason I want to do this is because the circuit I'm going to do right now is actually what we're going to use to do our advanced analysis. Okay. All right, so let's just throw some numbers up here. All right, one here, there, and this is my usual go-to one because it's nice, it's easy, it's got all the parts that we need to make this work. Okay. So make this 12 volts. Make this 8 volts. We'll call this 400 ohms. And we'll make this 200 ohms. Make this one 300 ohms. All right, so that's my circuit. Nice, pretty simple. All right. So for superposition, all right, we solve the circuit one source at a time. I always just move left to right. So my recommendation when you do this is always redraw the circuit. Now, I'm doing the 12 volt source. So we got 400 here, 200 here, 300 here, and then I replace the voltage source with a short. So the neat thing about putting a short in there is what? Well, we end up creating relationships between resistors that didn't even exist before. In my original circuit, none of those resistors were either in parallel or series with any of the other resistors. So there was nothing I could do to simplify. Okay. Now, I have the 300 and the 200 are in parallel, right? Because they're both connected to the same 2 points because of that short. Okay. All right, so 200 times 300 divided by 200 plus 300 is, what is that? 60,000 divided by 500, 120 ohms. So now that and the 400 ohm are in series. So my total resistance here will be 400 plus 120, which is 520 ohms, which will give me a total current of 12 volts divided by 520 ohms. Calculator here. Well, divided by 520. 23.08 milliamps. Now, just to move things quickly here, let's say the only thing I want to know is what the voltage is across the 300 ohm resistor. That's all I want to know. All right. So, in order to do that, I can either find the current through it and use Ohm's law, or just find the voltage. I'll just find the voltage because that's pretty easy to do. So with this contribution, the 12 volts, I'm looking for that voltage. That 12 volts is going to be divided between 400 and this equivalent resistance of 120. So the voltage across the 300 ohm resistor will be the 12 volts being divided times 120 ohms, it's there, divided by the total resistance dividing it, which is 520. So that's my voltage divider formula. I could have just taken the 23.08 milliamps and multiplied it by 120, because that came from 12 divided. This is where, with series parallel circuits in general, there are multiple ways to get there. Okay? So whichever one works for you is fine. But either way, this ends up being 2.769 volts. Remember, I normally want my answer in how many significant digits? 3. My final answer. But when we're doing things like superposition, where we may be subtracting numbers, I like to throw on a 4th significant digit in case I have to subtract. Okay? All right. So now what? Well, now I do all this again, but with the 8-volt source. And this time replacing the 12-volt source with the short. All right. So now, again, I have 2 resistors in parallel, different resistors this time. All right. So 400 in parallel with 300. All right. Product over the sum. I'll just add it in my mind there. I can do that sometimes. All right. So that gives me a resistance of 171.4 ohms. Okay. Now, that will be in series with the 200 ohm resistor, and that will divide the 8 volts. So I can go ahead and skip ahead here. The voltage across the 300 ohm resistor, right? And notice this will be the polarity because that's my direction of current, will be 8 times 171.4 divided by the total resistance, which is 171.4 plus 200, so that's 371.4. .693 volts. Now, I made an assumption about my polarity, right? If I'd have guessed wrong, then negative, no big deal. Now, based on this, that adds to it, right? That's the same polarity. That's the same polarity. So they're both the same. So we just add those 2 numbers up. So we take 3.693 plus 2.769 we get 6.46 volts. Okay? Final answer. Now, the neat thing about this, and I've done this plenty of times in 113, right? I can take that one piece of information. What's the voltage across the 400 ohm resistor? Well, around this loop, plus 12 minus that equals 0. So it's just 12 minus that. So boom. That means here I have 5.54 volts. What's the voltage here? Well, now I do this loop, it's 8 minus that. That's 1.44 volts. Now that I have the voltages, I can use resistance to calculate the current. I can basically solve all the rest of the circuit from that one piece of information. Make sense? All right. Now, how are we doing here? Okay. So that's superposition. All right. Now I'm going to beat this circuit to death tonight. Okay. Which is okay. All right. Nothing wrong with that. So Thevenin and Norton, right? What were those theorems? Well, they were about replacing a complex circuit with a simpler circuit. And the idea was we pick a component around which we Thevenize. We pick a component around which we Nortonize. I don't know if that's a proper verb or not, but it works. All right. So when it comes to Thevenin and Norton, all right, what are we doing? Well, we are basically trying to find an equivalent circuit around a component. So in this example, since the component I want to learn about is that 300 ohm resistor, that's the one that I'm going to Thevenize around. Right? Makes sense, right? Because what are we going to do? We're basically going to Thevenize around it. And for the Thevenin circuit, we're going to get a Thevenin voltage in series with a Thevenin resistance. If I Nortonize, I get a Norton current in parallel with a Norton resistance. All those are what? It's a real voltage source and it's a real current source. So whichever one I figure out, I can go back and solve for the other one, right? If it's easier to find a short circuit current, find a short circuit current. It's easier to find an open circuit voltage, find an open circuit voltage, right? If both of those are easy, I can use those two to calculate what the resistance is. Because what's true about the Norton resistance and the Norton current? I'm sorry, resistance. What's true about the Thevenin resistance and the Norton resistance? That's what I meant to say. They're the same, right? Remember, source conversion and resistance doesn't change. Value just changes where it is. Okay? So, what we do in terms of, and I'll get through this and we'll take a break. Okay? Okay. All right. So we're going to Thevenize around our 300 ohm resistor. So what that means is I remove it. Okay. Take it out. So I'm looking for 12 volts, 8, 400, 200. So what am I doing? Well, if I'm Thevenizing, I'm looking for what the voltage would be between those 2 points with nothing there. Now, it's not too hard to do in this one, right? Because by removing this, what kind of circuit do I have? It's a series circuit, right? Has a total resistance of 200 plus 400, 600 ohms. Now, is this series opposing or series aiding sources?
Opposing?
They are opposing, right? Because one wants to make current go clockwise, the other one wants to make it go counterclockwise. All right, so the net voltage is 4 volts, right? So the total voltage is 4 volts. Total resistance is 600 ohms, which gives me a total current of 4 divided by 600, which will be 33 point lots of threes. Oh no, sorry. 66 point lots of sixes milliamps. Right. Is that right? 4/3? 4 divided by 6? 2/3, right? All right. I have to be careful when I'm doing this off the top of my head. Yeah, that's why it's good to check. 6 point. Had decimal in the wrong place. 6.667 milliamps. There we go. Okay. Now, that flows through 400 ohms. It's a voltage drop of 2.66666. Now, because this is bigger, current flows that way. So there's your voltage there, 2.667 volts. And then this will just be half of that, because it's half the resistance, 1.333 volts. And those two, of course, add up to 4. So what is the voltage between these 2 points? Well, we can use our Kirchhoff, right? Start here, plus 12, minus 2.667, minus V, back where I started, equals 0. Or go this way, and it would be plus 8, plus 1.333. Either way, it's 9.333 volts. That is your Thevenin voltage. Okay. Just to play both sides here. If I had done all this, and instead of looking for the open circuit voltage, right, I still remove the part. All right, the part's still gone. But now, if instead I put a short there, find current. That short circuit current is the Norton current. So how do we do that? Well, in this case, I have, because of that short, I have 12 volts across here. And because of that short, I have 8 volts across there. So that's going to be what? 8 divided by 200 will be 40 milliamps. All right. 12 volts divided by 400 ohms. That would be 30 milliamps. Right? So that's coming into this point. That's coming to this point. They add together. So my Norton current is 70 milliamps. Make sure I did my math right. Yeah, okay. Right? Now, I can actually use those two numbers to find the Norton and Thevenin resistance, but let's just show you how you do it. So to find the resistance, I basically remove the component and I look for the resistance between those 2 points, replacing all the sources with their ideal internal resistance, which, since they're both voltage sources, are shorts. So now as a result, the 400 and the 200 ohm resistor are in parallel, right? Because I'm basically saying come in here and get back to there. So when I come in there, I have 2 paths. So they're both connected to that point. Because of the shorts, they're both connected to that point. Boom, parallel. So my Norton and my Thevenin resistance use the same method to calculate the resistance. That's why they're always the same. Okay? It's going to be 400 parallel with 200. So that'll be 800 divided by 600. So that'll be 133.3 ohms. So if I had taken the Thevenin voltage and divided by the Norton current, 9 point lots of threes volts divided by 70 milliamps, any guesses what I would have gotten? Well, 9 point lots of threes divided by 70 milliamps gives me 133.3333 ohms. Same thing. Now, that's the Thevenizing, that's Nortonizing. What do you do with it? Well, we take our, since we're looking for voltage, I'm going to use the Thevenin equivalent circuit, which is 9.333 volts in series with 133.3 ohms. And then that component we took out, that 300 ohm resistor, put it back in. Now, solve for the voltage. Well, that's a voltage divider. So the voltage across the 300 ohm resistor will be 9 point lots of threes times 300 divided by the total resistance dividing it, which is 300 plus that, or 433.3 ohms. What do you get? 9 point lots of threes times 300 divided by 433 point lots of threes, 6.46 volts. Well, look at that. Exact same thing that I got over there. How's that for a review? All right, that's a whole semester in just over an hour. Well, actually, no, less than an hour because I spent some time talking about this. All right, questions? That's not review. I'm going to skip to maximum power transfer because that's the one that's just a little bit different when we get there much later this semester. All right, so let's take a 10-minute break, come back at 6:30 after the hour there. We're going to solve this circuit 3 more times. 3 different methods. And we better get the same thing every time. All right. Ready to have some more fun?
Is time to play video games?
No.
Still not fun.
All right. So what we're going to do is basically look at 3 different methods for solving complex circuits. And that could include circuits with 2 sources or more. It could include circuits that have no resistors in parallel or series. Because if we can't do that, that's all we learn, right? Now we've learned a number of methods with multiple sources, right? Superposition, I can use source conversion, a lot of different ways. But these 3 methods are basically going to use 3 laws. Ohm's law, Kirchhoff's voltage law, Kirchhoff's current law. That's it. Okay? That's it. So yeah, same circuit. Now when we look at this circuit, three methods we're going to use. Mesh analysis, branch analysis, and nodal analysis. Okay. Now, let me just put those up here real quick. Okay. So branch, mesh, nodal. So when we look at this circuit, the idea behind branch is to identify how many different currents there are in this circuit. How many? Nope. In other words, how many branches are there?
3.
3. Okay. Right. You got the one on the left there with the 12 volt, the 400 ohm resistor in series. That's one branch. That 300 ohm resistor all by itself is another one. And then, of course, on the right, the 400.
The 8 volt with 200.
Or 200 in the 8. Okay. Now, what the branch analysis is going to do is basically assume those 3 currents. In other words, draw the currents, choose a direction, right? And then solve for those 3 currents. Now, mesh analysis does the same general thing, except instead of looking at individual branches, you're going to look at windows. Think of a window pane, right? And within any particular window pane, you're going to have a circulating current. So when I look at this circuit, how many window panes are there? 2. So we would look at those 2 currents. We would make our assumption about which direction they are, and then solve for those 2 currents. Now, nodal analysis is going to involve determining how many different nodes there are, because every node, I can basically find the voltage between 2 different nodes, right? 2 different points. So a node is a point. It's a point of intersection between components, branches. So how many nodes are in that circuit? 6. Nope. Anybody else? I didn't mean to shoot you down that fast. I just know the right answer.
I want to say 2.
Nope.
Okay.
Higher than 6?
Nope.
Nope.
4. All right. You just take 2 and 6 and go in the middle. Or
I don't
right.
know.
So basically, we're looking at points, right? Well, there's 2 obvious ones.
Yeah, that was what I was going off of.
That's another one,
Okay.
and that's another.
Oh, so the point in between them.
Anywhere components are connected together.
That makes
I added the 2 on the bottom, but there's nothing there. So I assume
Yeah. All right. So what does that mean? Well, that means that I have 4 different points, and what I do is I select one of those points as a reference. Well, what's the voltage at that point going to be then, if I call that my reference point? 0. So I identify one of those nodes as a reference point, and then I write equations regarding the other 3 in this case. Now, that sounds like 3 equations, for 3 different points. Well, you never know, right? Depends on what's in the circuit. And that's the fun part about this. So what we're going to do is we're going to use each of these 3 methods to solve this circuit. Start with the easiest one to visualize because it's fairly basic, right? And that is branch. Now, when I draw these currents, we already know the direction of all the currents, right? So one thing I'm going to do for fun is I might guess wrong. What's the point of guessing wrong?
A step closer to the right answer.
What's that?
It's a step closer to the right answer.
But I mean, what happens if I guess wrong?
I'm just saying. Well,
Let's go back real quick. All right. Kirchhoff's voltage law. If I didn't know the polarity of something and I guessed, what happens if I guess wrong? Got a negative result. That's it. All right. That's it. All there is to it. Okay. So you don't have to know. You know, like when I do mesh analysis, I always just draw my currents counterclockwise. Or no, clockwise. I always do clockwise.
Because it just boom. It's
Just the way I do it. All right. And the answer will all work out in the end. Trust me. All right. Now, for branch analysis, I have to make assumptions about current. I'm going to keep it simple initially here, since we have a pretty good idea, right? We could guess that in this branch, because of the polarity of my voltage source, we would guess that that current's going to go that way. We'll call that current 1. Likewise, I would guess that that current's going to go that way. I'm just going to go 1, 2, 3. So that's my current 3. And then just because that's my 2 guesses, those 2 are going to combine. And so I would guess that that third branch, or my second branch, if you go left to right, is going down. Again, if I guess wrong, it'll tell. Okay. All right. So once I get a current direction, all right, we know that what? That's the polarity for the voltage sources. And based on this current direction, 3 individual currents, that will create a voltage drop with that polarity and that resistor, this polarity in that resistor, and this polarity in that resistor. Make sense to everyone? Okay. Well, now that I have voltages and polarities, what do? Kirchhoff's voltage. Now, I have how many loops that I can do? How many loops can I do? How many different paths can I take? You got 2 panes, right? This is kind of lends itself toward mesh, right? So don't quite, they're similar enough. You go, yeah, there's 2. There's also what? If I just go all the way around the outside, that's 3. Right? How many unknowns do I have? 3. Current 1, current 2, current 3. 3 unknowns. How many equations do you need to solve for 3 unknowns? 3 equations. Now, I got bad news. Not quite that simple, but let's just go through it. All right. So Kirchhoff, right? So equation number 1, start here. Plus 12 minus current 1 times 400. You know what? I'm just going to switch that around. 400 times current 1. All right. Minus 300 times current 2. And back where I started, so what's that equal to?
is not 0.
Yes,
Oh.
0. Get back to where I started, it's 0. Closed loop. Right? Now, let's do this one. I'll start here. Plus 300 times current 2. Plus 200 times current 3. Minus 8. Back where I started, so what's all that equal to?
0.
0. All right. Now, third equation. it'd be nice to just say, yeah, we'll just go around the outside. Well, anybody know anything about solving 3 equations and 3 unknowns? How do you do that? How do we do that? Well, here, let's go ahead and do it. We'll do the outside just to make my point. So that's equation 1, that's equation 2, third equation, we'll go around here, plus 12 minus 400 times current 1 plus 200 times current 3 minus 8. Now I'm back where I started. All that equals 0. So let's simplify my equations. I'm going to put them in a standard form. All right. So my standard form will be, let's see, those are all negative. So if I move those to the other side, I have 300 current 1. Right, 300 times current 1. No, current 1 is 400. Come on. 400 times current 1 plus 300 times current 2. There is no current 3. And then moving those over there became positive. That equals 12. Second equation, I have a 300 times current 2 plus 200 times current 3. Move that to the other side, 8. And then my fourth equation, we have minus 400 times current 1 plus 200 times current 3. Okay. And then what? 12 minus 8 is 4. So we move that to the other side, negative. All right. Now, how do I solve this? How do you solve multiple equations, multiple unknowns? A couple different ways you can do it. One is substitution, right? If I can, solve one of the equations or one of the unknowns in terms of the others, substitute that into the equation, go from there. That gets ugly, that gets messy, especially 3 equations, 3 unknowns. Guess what? I don't want to do that. So here's what I offer. Anybody familiar with The Matrix? I don't mean the movie. It's fun because I actually just rewatched that movie last week.
Yeah, I thought you talked about Matrix. So I was going to say.
I was having internet problems and I wanted to watch something. It's like, all right, what do I got on DVD? Oh, Matrix, cool. All right, yeah. So here is what we're going to do to solve this. Okay. I didn't hear it start up, so I'm like, what's going on? All right. I will show you here. All right, when I activate your module 1 after class, you will have access to this Excel spreadsheet, which I entitle Matrix Solutions. So what that involves is setting up a matrix, which is a 2x2, a 3x3, a 4x4 grid. And we put in values. And when we do that, you can find the determinant of the matrix. And when you substitute in, so the initial matrix is going to be the values for current 1, current 2, current 3. That's why I set this up, right? Because basically, that's your input, all right? And then you take the constants and you substitute them in to each unknown that you want to solve, the I1 column, the I2 column, the I3 column, solve that determinant, and then take that value of those 2 determinants, divide them, and that's your answer. Now, it's messy, it's complex, which is why I did this. All right. So I download my matrix here. I'm going to open it with Excel. All right. And this is a 3x3 matrix. There are three unknowns. All right, so I have enable editing here so I can put the numbers in. All right. And so when I fill in this matrix with the values for current 1, current 2, current 3, and my constant, the answers will come out like that. Okay. So let me do that real quick with what we have here. All right. So my first equation, 400, 300. What do I put in for current 3? Well, there was no term, 0. All right. And then my constant for that one was 12. Second equation, there was no current 1 term, so that's 0. 300, 200, and my constant was 8. Okay. For my third equation, current 1 was negative 400. Current 2 was 0. Current 3 was 200. And my constant was negative 4. And what do I get? Nothing. Why? Anybody want to hazard a guess? Problem is that third one where I ran around the outside, I'd already gone around those components with the first two equations. It didn't add any new information. What do? I need a good third equation. All right, so what am I going to do? Well, let's go back to the circuit here. This didn't work. Didn't add any new information. Well, that was all using Kirchhoff's voltage law. What else do I have? I also have Kirchhoff's current. What's Kirchhoff's current law tell me? Algebraic sum of currents at a point equals 0. So if I choose this point, I have current 1 coming in. Current 2 is leaving. That's a negative. Current 3 is coming in. That's the algebraic sum equals 0. There's your third equation. All right. So now, come back here to my matrix here. So instead of putting in those numbers, I'm going to put in a 1, a negative 1, a 1, and a 0. Done. All right. There's your answer. All right. Now, in my case, I was looking for what? The voltage across the 300 ohm resistor, which has current 2 flowing through it. Okay. So if I want to know, in this case, voltage 2, I could just say, well, that's going to equal that current times 300 ohms, right? Because I put all the resistances in ohms, that means all the currents are in amps. If you put all the resistances in kilo ohms, all your answers will be milliamps. You just have to be consistent. Don't mix it up. So when I do that, I get 6.46 volts, which by now, after having solved this twice already, you should remember that, yep, that's the answer. Pretty cool, right? Makes sense to everyone? All right. Now I'm going to leave this up here because I'm lazy. I'm going to come back to it, right? I actually have here a 2x2 matrix, 3x3. I go all the way up to a 9x9. You could literally put in 9 equations with 9 unknowns, and this will give you the answer. You won't need it. I just got carried away. I couldn't stop. All right. Now, any questions on that? Okay. So this was branch analysis. All right. So now, let's get rid of that. So this one's going to get a little trickier. Polarity of my sources doesn't change. So now we're going to look at mesh analysis, right? Mesh analysis. So with mesh analysis, the currents we're going to draw are what are going to circulate in those panes that I talked about. So we said earlier we had how many panes? 2. All right. So I'm going to draw my circulating currents. This is where I'm going to start to guess wrong. I always draw my currents clockwise. 1, 2. So how many equations do I need? For 2 unknowns, how many equations do I need to come up with? 2. Well, that makes it nice, right? Because I already know how to draw 2 equations because I have 2 loops to go around. Here's the tricky part, or here's the part that is just a little bit different. All right, you'll see it here in a second. So, equation number 1. Start here. Plus 12. Again, based on the current direction, I'm going to get a polarity. Well, here's the tricky part. Current 1 and current 2 both go through the 300 ohm resistor. Current 1 creates that polarity, but current 2 is going the other way, so it creates that polarity. Both of them have to be included. I'll show you how we do that. All right, so plus 12 minus 400 times current 1. Okay, now what's the voltage across this resistor? Well, there are 2 current contributors. Minus 300 times current 1 and plus 300 times current 2. I'm back where I started. Okay. Now, second equation, second loop. I'll start here. Now, again, the 300 ohm resistor has 2 contributors, right? Plus 300 times current 1 and minus 300 times current 2. Minus 200 times current 2 minus 8. Back where I started. So now we'll do the same thing. We'll combine the terms, set everything up here. When it comes to combining terms, I'll leave the negatives. I don't care. And they'll just do it because it won't matter. All right. But when you're adding everything up, when you start changing the same signs, you can mess things up. So for current 1, I have minus 400 minus 300, so that's minus 700 times current 1 plus 300 times current 2. My constant goes over there, negative 12. Here I have 300 times current 1 minus 300 plus minus 200 or minus 500 times current 2. My constant moves over there, becomes positive. That's it. 2 equations, 2 unknowns. Now, real quickly, let me come back to my 3x3 matrix here. Even though I didn't need it, let's just note here, current 1, 13.85 milliamps, okay? That's going to be the same current 1 here, right? Current 2 was in the 300 ohm resistor. Current 3 is about 7.69 milliamps. Well, that's going to be the same as current 2 here, except it's going the wrong way. Okay, make sense? So I'll leave that there. We'll come back. So my 2x2 now, my constants are negative 700, 300, negative 12, my current 2, 300, negative 500, and 8. So there you go. 13.85 milliamps for current 1, exactly the same. Current 2 here is equivalent to current 3, but going the wrong way, so it is a negative. Now, when it comes to doing the calculations, right, again, what was I looking for? I was looking for the current in, or the voltage across, the 300 ohm resistor. Well, that's always fun for this type of analysis because, well, that's actually 2 voltages. Positive here, so it'll be current 1 times 300 ohms will be part of the contribution. And then negative 300 times current 2 will be the other part. So you got to add those up. Well, negative times a negative becomes a positive. Okay. And so in terms of using this to calculate it, you could also just do the difference between the two. All right. So if we look at the difference between the two, then the current in the 300 ohm resistor will simply be current 1 minus current 2, 21.54 milliamps, which when you go back to here is exactly what we had for our current 2. So even though this is a little simpler in terms of finding the equations, 2 equations, 2 unknowns, pretty straightforward, you have to take the data you get and then massage it a little bit, all right, and to get everything you need. So it's a little trickier, but you know, it's a choice, right? You got 2 so far. Now we're going to do a 3rd. Right? We get the same result. You know, when we get the difference in the current, and you take that and you multiply that current times your 300 ohm resistor. Boom. Oops. Sorry. Oh, plus times 6.46 volts. Okay. All right. 2 down, 1 to go. So my 3rd method is nodal. So what I'm going to do get rid of these again. Okay. All right. So the first thing I need to do, the first thing I'm going to do is I'm going to label my nodes. So as we said earlier, we have 4 nodes, right? So I'm just going to call them A, B, C, and D. Because I can basically use that information, all right? I can use that information to figure out current. Because between some of those nodes are resistors. Those are points. The potential difference between 2 points is the voltage. You got a voltage, you got a resistance, and calculate the current. Now, that means that I need to figure out my currents. So very similar to my branch analysis, how many currents do I have? Different currents do I have? 3, right? 3 different currents. Okay. Now, just for fun, I'm going to go ahead and tell you that all my currents are flowing into point B. Now, I know that's wrong, but like I've said before, it's not going to matter. Okay, not going to matter. Now, I'm going to label these currents: current 1, current 2, current 3. So, by having those 3 currents, we'll set up our equation by saying what? Well, Kirchhoff's current law says the algebraic sum of currents at a point, since they're all coming in, they're all positive. equals 0. But here's the difference. I'm now going to define each of those currents based on the information in each branch. So, based on that current direction, these are my polarities of voltage across those resistors. Because what is voltage? It's the potential difference between 2 points. Now, what is the voltage across the 400 ohm resistor by that definition? What's the voltage across the 400 ohm resistor? It's the voltage at point A minus the voltage at point B. Because that's what that resistor is connected between those two. Okay? So based on that polarity, I can define current 1 as the voltage at point A minus the voltage at point B divided by 400 ohms. Make sense? Okay. Now I'm going to make you guys work here a little bit. So based on that, what is current 2 equal to? So that same technique. Exactly. All right. The polarity tells you which numbers to subtract, right? So the plus is where we start, voltage point D minus voltage point B, and it's a 300 ohm resistor this time. All right, what about current 3? Was that Andy?
Jose said you got it.
All right, Jose, what's current 3? Okay. Okay. Exactly. All right. All we did was what? Our definition of voltage, determine voltage, divide by resistance. That's Ohm's law. All right. Now, so far though, that's how many unknowns do I have? I got 4. Right? Voltage A, voltage B, voltage C, voltage D. But what did I say I'm going to do? I'm going to choose one of those as a reference, which is going to make that voltage what? 0. All right. Now, do you think it matters which one I choose? It won't matter. But if I choose good one, I can potentially then also know the voltage at other points. And really, it doesn't matter which one. Literally do this, whichever one. The way this circuit is. Now, that may not always be true for all circuits, but for this one, it really doesn't matter. Who wants to choose a reference node? What's that? D? All right. So we're going to make D a reference node. All right. So I'll clarify that by putting a ground symbol there. Why not? Right? That's a reference point. Okay. So that means the voltage at point D is 0. Now, why did you choose point D?
Why did I choose?
Yeah.
Because I originally I thought the right answer was B. I don't know. I just chose B to see if that's right.
Yeah. D is I mean, like I said, could literally choose it. But that's a good one. Right? Because why? Because also connected to that point, what do I have? I got 2 voltage sources. So who can tell me what the voltage at point A is with respect to ground? Go ahead. No. 12 volts. Because between point B and ground is a 12-volt source. Okay? So now, This is one less unknown, right? Voltage at point A, 12 volts. What's the voltage at point C?
8 volts.
8 volts. There's another unknown gone. How many unknowns do I have left? One. So I'm going to end up with one equation. One unknown. So let's set that up. And what I'm going to do is I'm going to take these three things here, put them in there. That's going to be my final equation. All right. So current one is voltage at point A, which is 12, minus the voltage at point B, which I don't know, divided by 400. That's current one. Plus, this is one reason I like to do this, right? No negatives this way, right? And you know, negatives just really mess you up. All right. What's current two? Well, current two is voltage at point D, which is 0, minus the voltage at point B. Well, shoot, I ended up with a negative. Why? If I'd drawn the current the other way, that would have been a negative anyway, because that current would have been leaving. Didn't matter, fixed itself. Divided by 300 plus current 3. Well, current 3 is the voltage at C, which is 8, minus the voltage at B, divided by 200. And all of that, we'll see. So now I have what? One equation, one unknown. Now, easiest way to solve this, you heard of what? Least common denominator. What would I use here?
Least common denominator. For the 400 and 200 ones, you can multiply the. You could divide the 400 one by 2 and multiply it by 3. I know what I'm trying to say, but I don't know how to explain it.
When I look for my least common denominator, or what I'm looking for is one number I can multiply this whole thing by and get rid of the fractions. That's too long. 1,200. You see it? Right? 1,200 divided by 400 is 3. 1,200 divided by 300 is 4. 1,200 divided by 200, 6. All right. So if I multiply all that by 1,200, well, 1,200 times 0 is still 0, so nothing changes there. All right. Now, 1,200 divided by 400 is 3. So I have 3 times 12, which is 36, and then times negative, and then times negative b gives me negative 3b. So that's that term. 1,200 divided by 300 is 4. So now I just have a minus 4 voltage b, right? Minus there. And then 1,200 divided by 200 is 6. 6 times 8 is 48. Minus 6. 0. Okay. All right. So I have a negative 3, a negative 4, and a negative 6. So that adds up to negative 13. I have 36 plus 48. That adds up to 84. So to solve this, move that to the other side, becomes positive. Voltage B will simply be 84 divided by 13. And so when you do that, okay, calculator up here. 84 divided by 13. Any guesses what we're going to get? Better be 6.46, which is exactly rounded to 3 C. Pretty cool, right? Ready to really put this to the test now? Yeah, I didn't even need that, right? Guess what I have here? Well, sort of. Slab number 1. For homework, will to basically calculate the predicted voltage for all those resistors and the predicted current. Now, let me just do a quick example with other numbers. I don't suppose, Dylan, you don't have your 113 notes with you, do you? I was just gonna go ahead and do the, because what is that circuit that I handed out to you?
The one you handed out right now?
But remember what I called that?
Not quite.
It's basically a Wheatstone bridge. All right, except it's a loaded Wheatstone bridge. Okay, therein lies the problem. Okay, I don't remember anymore. We'll make one up. 10 volts. So I'll just throw in some numbers here. 300, 700, 400, 600, and we'll make this 200. Okay. Now, when I did this in 113, when I first put this up, something similar to it, I couldn't solve it, right? Because why? None of those resistors are in series or parallel with anybody else. How did I end up solving this in 113? I feminized around a complement. True to form, everybody chose the wrong one to feminize around. I don't know if you guys remember this whole exercise, right? Okay. Because feminizing around the wrong one doesn't get you the wrong one doesn't get enough information. What's the wrong one? Well, there's only one up there out of those 5 that is the wrong resistor to feminize. So that was fun, right? But we're going to use what we just learned to solve this circuit. So let me ask this question. How many branches are there in this circuit? How many different currents, right? That's what the branch analysis does, right? Different currents. How many different currents are there in this circuit?
4.
Nope. 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 6. Nobody's in series. Nobody's in parallel. There are no shared currents. There are 6 components up there. There are 6 different currents. Okay? So to use branch analysis, you would need to come up with 6.
You can trust bullet points. Oh, I see 4 of them, but I'm missing 2.
What do you mean?
The 2.
I'm going to have a current for this one.
I'm talking like with the points.
Well, I'm not to the points yet.
Oh, that's fine.
I'm still doing branch. We're talking
Right,
branch.
6,
We'll get there. All right, we'll get there. So, branch analysis. 6 different currents. I have to come up with 6 unique equations, right? Because if I repeat an equation, it won't solve. That'd be unique. I'll tell you right off the bat, that's true. How many circulating currents do I have? In other words, how many window panes? Using mesh analysis, how many currents am I talking? Three, right? Three panes, right? So I can do that with three circulating currents. How many nodes? Nope,
Oh, this is what it's for. It's,
four.
I was thinking.
You jumped ahead.
Yeah.
Okay, there are four nodes. So if I choose one of them as a reference node, that will not be known. And because there's a voltage source between that reference node and another node, that will be another known voltage. So how many unknowns did I end up with? Two. I only need how many equations then? Well, I shouldn't say that. It's not two equations, two unknowns. Right? It'll come. It will come. All right. So, which one do we want to do? Well, I'm lazy, and we're running out of time. I'm going to do no. All right. So I'm going to kind of go with a foregone conclusion here that I'm going to call this A and call this B. I'm going to use this as my reference, and we know that the voltage here is 10 volts. So I'm kind of skipping ahead, if you will. All right. Now, how many currents am I going to have to use to get this? This is where it gets fun. We know how many currents are up there. Branch analysis, there are 6 different currents. How many can I actually write an equation for? In other words, how many of those currents have resistors between 2 poles?
5.
Only 5, exactly, right? Because the current in the source, the 10-volt source, there's no resistor in there. There's nothing I can use to figure out what that current is. All right. So based on that, I'll just go ahead and make my assumption here that this will be current 1. We'll call that current 2. I'm guessing the directions here, hopefully accurately, current 4. Now, what about here? Which direction is that current going to go? Left to right or right to left? Any guesses? Based on the values that I have here? I'll give you a hint. If this resistor is not there, I can actually solve this circuit, right? With respect to ground, the voltage here would be 7, the voltage here would be 6, and when I put the resistor in, that means the current will flow that way. Okay? So, the key on this, all right, what it comes down to, even I didn't make it obvious last time, right? Because it was a fairly simple circuit. Well, I'm going to end up solving for 2 nodes. Well, what are nodes? They're points. So because I have 2 nodes, I can write 2 different Kirchhoff current. Okay. Now, let's go ahead and figure out what our currents are. Right? So current 1 is what? Same technique we just used. Okay. Based on the current directions, I'll put the polarities up here, right? Just to clarify. Because the polarities are all based on my assumed current directions. Now, I made a point of actually assuming as correctly as I can here. Right? So, current 1 will be the voltage up here, which is 10, minus the voltage at point A, divided by 300. What's current 2? Anybody? What's current 2? Right there.
Yeah.
What's the voltage across that resistor?
Wait, 10 volts.
Nope.
No.
It's the voltage across this resistor. For your polarity, it's voltage A minus zero. Didn't say it.
Oh,
Get a little
So it's just voltage A divided by 700. Okay. All right, what about current 3? What's that? Three's up here. The plus is where you start. That is 10 volts. Minus voltage B divided by 400. How about current 4? It's current 4. Jose? You read everything from back there? Okay, current 4 is right there. With the voltage between those 2 points. That's where that resistor is. Voltage B minus 0, so that'll be just voltage B divided by $600. Okay. And then finally, current 5. Ben, you want to give it a shot?
A minus.
All right, exactly. Okay, because of the way I drew the current direction, polarity. Okay, so now what? Well, I have 2 nodes. So node A, if I look at node A, what is my Kirchhoff's current law? Well, I always say anything coming in is positive, so I have current 1 coming in. Anything leaving is negative. So minus current 2 minus current 5. That's my algebraic sum. That's it. At node B, I have coming in current 3 plus current 5 minus current 4 leaving. That's my algebraic sum. That's equal to 0. Now, I take and substitute in my 3 currents for each one. So current 1, 10 minus voltage A divided by 300 minus current 2, which is voltage A divided by 700 minus current 5, which is voltage A minus voltage B divided by 200, and then that's equal to 0. Same thing down here, right? Current 3, though, is 10 minus voltage B divided by 400 plus current 5, so we just did current 5, voltage A minus voltage B divided by 200 minus current 4, which is voltage B divided by 600, and that's equal to 0. So now we do the same thing we just did, all right? Least common denominator here. Anybody? Well, one thing about 2, 3, and 7, they're all prime numbers. Okay, so you don't get any freebies there. So 3 times 7 times 2 is 42. So we'll just do 4,200. Okay. And then what about here? 400, 200, and 600. Oh, that sounds familiar. Didn't we have those same numbers?
Yep.
Wow, that's freaky. What was that? Common denominator was 1,200. Okay. All right. So now we're going to get equations here. So 4,200 divided by 300 is 14. 14 times 10 is 140. Minus 14 times voltage A. 4,200 divided by 700 is 6. So I have minus 6 voltage A. 4,200 divided by 200 is 21. So I have minus 21 voltage A. Minus a minus becomes plus 21 voltage B. Anything times 0 is 0. So you got to be careful when you're, that's why you got to be careful of those negatives. All right, here, 1,200 divided by 400 is 3. So I have 30 minus 3 times voltage B. 1,200 divided by 200 is 6. So I have plus 6 voltage A minus 6 voltage B. 1,200 divided by 600 is 2 minus 2 voltage B. So now we combine our terms. All right, what do we got here? Got 140. That's it. So move that to the other side, becomes negative 140. Voltage A, I have negative 14, negative 6, that's negative 20. Negative 21 is now negative 41. So minus 41 voltage A. And the only voltage B I have is plus 21. Okay. Here I have 30, so move that to the other side, becomes negative 30. I have 6 voltage A, that's it. Voltage B, I have minus 3, minus 6, which is minus 9, minus 2, which is minus 11 voltage B. Now, that's my setup, 2 equations, 2 unknowns. So even though this is labeled, it doesn't matter whether it's voltage or current, all right? Whatever I put in, I'll get the answer, right? So when I put in all these numbers, what I will get is a voltage, 2 voltages, right? All right, so let's clear this out. That. Okay. All right, so current one is voltage A. All right, it's your spreadsheet. When you download it, if you want to mess with it, that's fine. All right, you can change it. All right, so voltage A, negative 41. Voltage B is 21. My constant is negative 140. In my second equation, voltage A is 6. Voltage B is negative 11. And my constant is negative 30. Okay, and there you go. So those are my answers. What are the answers? This was voltage A, voltage B. So voltage A, 6.677 volts. Voltage B, 6.369. There you go. All right. So now, for your lab, what you're going to do, all right, is you're actually looking for the voltages across all the resistors. So the voltage across this resistor would be voltage A minus voltage B. The voltage across this resistor is voltage A, voltage B, 10 minus A, 10 minus B. There's your voltages. Or you just take those voltages, plug them in with circuits and get currents, right? Because I asked for both the voltage and the current. That's the easy way to do it. Of course, your numbers will be different because the resistor values are different. And here's the bad news. These common ground, they're really going to suck for you. But hey, that's the fun part of it. All right. So what I want you to do on the back is show your work, right? Show your work on the back. So I just demonstrated nodal. If anybody wants to do branch or mesh, I'll give you some bonus points. You gotta show me the equations though. All right, questions. Hopefully we had a really good review of 113. All right, no homework other than preparing for lab 1, which is kind of doing this. Right?
I gotta find the book.
And next week we start chapter 10. We'll redo chapter 10, however you want to call it. Yes.
You okay? Sounds like you're dying though for a moment.
Hey, I haven't talked. I haven't lectured in 4 weeks.
Yeah.
All right. This is a lot of talking for one day. I got to do it again tomorrow. My only advantage was I didn't have to do it on Tuesday. Lucky me. All right. There are no questions. The rest of the time is yours.